This presentation is the biomechanical analysis for improved sprint training. This will be based on performance analysis of how to actually improve sprint times based on training and some key variables that deal with training and performance. Overall sprinting techniques is divided into 5 stages: the early phase, mid-flight, late flight, early support, and late support in the overall sprint performance. Early flight phases include the eccentric hip flexion, eccentric knee extension, whereas mid-flight deals with more concentric hip flexion, and the late phase deals with concentric hip flexion and eccentric knee flexion that actually rotates the thigh backwards. Early support phases include concentric hip extension, a brief concentric knee flexion followed by an eccentric hip extension. Eccentric plantar flexion is also used for shock absorption, whereas in the late phase, eccentric hip flexion, concentric knee extension, and concentric plantar flexion all take place. In the video, you can see the flight phases and easily pick out the eccentric hip flexion that rotates the thigh backwards, the concentric hip flexion that accelerates the thigh forward, and the late flight of the concentric hip flexion that also rotates the thigh. During the support phase, you can see the early concentric hip extension that minimizes the brake effect at heel strike. Sprinting for performance deals with many variables including energy and work, power, forces, linear kinematics, linear kinetics, torque, angular kinematics, and angular kinetics. With energy and work is the product of force and displacement, whereas kinetic energy is mass and velocity each athlete possesses. This is key variables in performance for sprinting because the mass of the athlete and the ability to generate velocity creates a lot more power, and power can be generated within the concepts of work because of the speed at which work takes place. So overall, the maximal force that an athlete can exert will give you more fast-paced sprinting. In the video, you can see how power is generated by the mass of the athlete and the amount of force generated into the ground, which causes more velocity for this specific athlete. Improvements in energy and work really have to do with the way you train and how the power is mainly dependent upon different energy systems, meaning mainly the phosphagen energy system, and how training periodizations to build relative body strength and power through plyometrics can help the athlete be a lot more efficient in its energy production, conservation, and work and power output. Linear kinematics play a main role in sprinting for performance. Linear kinematics describe motion as speed and distance and direction, and it's relative to the position of the body where certain limbs are located in certain places in space, whereas motion is the action and the change of that position, and displacement describes that distance traveled. So we're really looking at the rate of motion and how can the athlete train to create better positioning of the body and create better rates of motion in order to get those distance traveled. Linear kinetics, on the other hand, are forces that cause the motion. In describing Newton's laws of motion, meaning no net forces act on an object, then no movement can occur. If external forces act that cause an acceleration, or if the forces exerted on another object, then the other object exerts the same force back in the opposite direction. That's sprinting to a T because the amount of force generated by the athlete pushes back on the athlete and gives them that acceleration needed. Torque is an important component of sprinting due to the turning effect produced by force. In this sense, it would be muscles pulling and creating force, which in turn creates torques. So specific training components of getting the muscles to be more efficient will create more torque, therefore create better motion and better sprinting ability for the athlete. Angular kinematics deal with points of axis of the limbs and joints that provides the description of angular motion. Planes of motion become the relevance dealing with angular kinematics, because altering positioning of the muscle due to specific tightness or lack of recruitment can alter the success of the joint positioning. So it becomes imperative that we activate specific muscles and stretch certain muscles so that limbs and joints can get in better sprinting positions. In this slide, you can see the different planes of motion and the axis that go with those motions. As far as the joint actions themselves, you can see how different motions such as flexion, plantar flexion, dorsiflexion deal with the sagittal plane, whereas frontal plane deals more with abduction, adduction, lateral flexion, and the transverse plane deals with more rotations and horizontal adductions. Angular kinetics become relevant to sprinting due to the associations with the cause of angular motion. Knowing and understanding the cause of angular motion, in this sense, moment of inertia or mass and distribution of the mass, that can actually affect the sprinting technique and how successful the athlete can be due to his or her mass and that level of distribution and force that can be generated into the ground. So in a sense, changes in body position affect the overall sprinting outcome. From a qualitative anatomical analysis, we look at predominant muscular activity during specific phases of performance and look at the stresses that occur due to the muscle forces. In the analysis, we're mainly looking at hip, knee, ankle, and shoulder biomechanics and what motions occur at those joints, what muscle contractions are taking place, and what active muscles are actually contributing to the motion. In training, understanding these different motions and joint actions, we can manipulate training to transfer into better overall sprint performance. Looking at the hip biomechanics, we're looking mainly at the flexors from a concentric standpoint, meaning the psoas, quadriceps, tensor fasciae latae, sartorius, gracilis, pectinis, and from an eccentric standpoint, that goes from the downward leg phase of the sprint. In the extensors, we're looking at concentrics of the downward phase, meaning the hamstrings, glutes, and the posterior fibers of the gluteus medius. From the knee biomechanics, we're looking at the flexors in a concentric form that creates the upward phases of the leg. This would include the soleus, biceps femoris, semimembranosus, semitendinosus. Eccentrically, you look at the downward phases of the leg. Now in the extensors, from a concentric standpoint, this will create the downward phases of the legs, mainly in the quadriceps, and an eccentric portion would be more the upward phase of the leg. In this back-to-back video, we can look at the hip biomechanics and knee biomechanics and how all of that comes together with all the muscles. The ankle biomechanics may be some of the most important in sprinting due to the level of force generated into the ground with gravity. From a muscular standpoint, the flexors concentrically plantar flex at the takeoff, and the soleus, gastrocnemius, peroneals, and posterior tibialis and flexor digitorum longus may be responsible for this. Extensors at the concentric level is the dorsiflexion at heel strike, and this could be the tibialis anterior, extensor digitorum longus, and extensor hallucis longus. In this video, you can see the phases of the ankle and how it loads during sprinting. Shoulder biomechanics become important due to the propulsive effect that it gives in the upper body. From a flexor concentric shoulder flexion standpoint, we're looking at the pectoralis minor and anterior delts that creates that phase. Eccentrically at shoulder extension, there's a downward phase of the arm. Now in the extensors, concentrically at shoulder extension, the latissimus dorsi, posterior delts, teres major and teres minor may be responsible for that. And eccentrically, there's an upward phase of the arm during shoulder flexion. In this video, you can see how this athlete uses his arms and anterior delts and lats to propel himself through the upper body. Training for performance, we're looking at the positive effects of performance, the training parameters that are needed in three distinct phases: stabilization, strength, and power. Now, from a program design strategy, you need to know some of the biomechanics of technique, but as far as performance, we need to really look at how we periodize training through different energy systems, mainly the phosphagen system, and how we're going to progress the athlete to get into these better positions, strength-wise, muscle recruitment-wise, to get those joints in those better positions to affect all those variables discussed in this presentation. It's mainly linear kinematics and linear kinetics, and how we can generate more force and create more torques and more power generated into the ground. And that has to do with training specifically with a certain amount of mass and relative body strength, and how we generate that force into the ground to create these specific joint motions. During stabilization training, we can use muscle recruitment techniques to provide joint integrity, proper force couples, proper length tensions in the muscles compared to its agonist, and look at the neurological system and sensory motor system to see how efficient things get recruited. That's where the good sprinting technique starts, is being able to recruit certain muscles and get into certain positions overall. So the first stage, looking at stabilization, will provide a more efficient athlete to recruit muscles a certain way. We can use one-legged exercises, specific things that recruit the muscle in that effective way. Once stabilization is effective, we can go into more of the strength training portion, which in sprint, you're looking more at relative body strength in the legs and in the core. So a specificity of training using the different energy systems, mainly the phosphagen, manipulation of rest periods and tempos and sets, and the progressive overload will give you that adaptation to relative body strength, therefore increase in mass, therefore more force generated into the ground in order to produce better biomechanics and better physiology of adaptation and training. The final component in power training is a third phase from when the athlete becomes stable and becomes relatively strong. Now we can use that new strength using the stretch shortening cycle with plyometrics and being explosive and recruiting muscles fast. And the use of plyometric training, specifically jumps and hops and lunge jumps and explosive one-legged takeoffs and medicine ball training, can train the neurological system to have that transferability. So when you're looking at strength and power overall, yes, squatting and lunging is definitely what you need, but you need to take that new strength from the squats and lunges and be able to recruit those muscles fast and explode. That will create way better performance in sprinting and more force generated into the ground, therefore overall better sprint performance. That concludes the presentation on biomechanics for better sprint performing.